All right, dude, we are live. What's up, guys? This is Dem Keys, and today we're going to continue learning about Rust. And hopefully, today I don't get distracted again. What did I do after yesterday's stream? I'm trying to remember what exactly. Oh, yeah, I was doing more research on RF related stuff. I'm still very much interested in Meshtastic, and for a while now, I've been very interested in RF tech in general, be it something like ham radio or anything RF related. It's just the technology is super interesting to me, and what people have built on top of it using RF technology, what people have built, it's incredibly interesting to me. And the way that RF technology works, like once I found out about um what is it called? Long range, I think, LoRa. Once I found out about that, I did some more research and I was like, holy shit, dude. These signals are able to travel for probably like miles or kilometers in my case. They're able to travel for kilometers. Even if they're able to travel for hundreds of meters, that's still like really interesting to me. Give me a second. Let me go back to the thing that I was supposed to be at. Just a second here. Oh, wrong thing. Wait. Here I'm supposed to be here, and here I'm supposed to go back. Okay. Yeah, it is, dude, it is really interesting to me how RF technology works and how they have found different ways to communicate in both short range and long range. Like, holy shit, dude. It's crazy to me. And that's kind of why I want to learn more about it. Maybe at some point in the future I might be able to go down to the analog level. I doubt that's going to happen because there's like a shit ton of calculation involved with very low level RF stuff. At some point, I would like to get into it, but I should first learn analog electronics properly, and then I can get into um, doing bare bones RF. Which, I mean, to be clear, the only reason I would want to do bare bones RF is just so I can build my own custom circuitry to communicate on or to have access to very specific radio frequencies or frequency bands, very specific frequency bands that usually you don't get consumer hardware for. Or actually, I should check if you do get consumer hardware for even the restricted bands. I should look into that. Yeah, I should look into that. Another thing I could look into, and I could probably do this through, like, I could get one of those cheap. See, I'm doing this again. I'm getting distracted with um, other topics. But yeah, this is what I was doing research on yesterday because I haven't placed my order. I haven't placed the order for my items yet. I'm just finalizing the list, and I decided to remove speakers and amplifier modules from the list. And instead, I added three different types of RF modules. One of them, actually, I do have access to it already. Like, as in, um, one of them I do already have with me. Like, I have one of the types of RF modules that I'm looking for. Not specifically, maybe not specifically the module that I'm looking for, but something that is able to communicate on that frequency band. So the one that I currently have, it communicates on a 433 frequency, 433 megahertz frequency. And that seems to be an incredibly common frequency for your general purpose home electronics and stuff. And then there's another frequency band because 433 is incredibly common and so crowded. There's another frequency band which is 838 megahertz, which apparently more sophisticated systems use, stuff like alarms and security systems and stuff like that. So what I'm thinking of doing is, and this is why I'm so excited about RF stuff, dude. There's so much to explore. There's bare bones frequencies, right? Exploring bare frequencies, as in just 433 or 838. Another one was, I think, 915. I don't remember. Something in the 900 range. But I don't think I'm going to be touching that. Give me a second. My system, my internet connection seems to be having a bit of a hiccup. So I'm just going to try and reduce the load. Okay. Yeah, what was I saying? So you have the bare bones frequencies, right? You have the 433, 838, something in the 900 range. There's that. But then there's also the 2.1 gigahertz to 2.5 gigahertz range, where you have a bunch of higher tech stuff happening or higher level stuff happening, like Wi-Fi and Bluetooth, and I believe NFC and RFID also operate within that range, but I don't remember. Hold on, let me Google that. NFC RF range. No, that's not what I meant. I meant key characteristics, 13.56 megahertz. Hold on, is this not built for, is NFC not built for the 2 gigahertz range? Hold on, let me just open up a new Gemini instance and I can have a conversation there. Hey, so I was assuming NFC and RFID are within the same frequency band as Wi-Fi and BLE, which is Bluetooth Low Energy, which is around the 2 gigahertz range. Is that wrong? This is a very common assumption because all four technologies are found in our phone, but that is actually not correct. While Wi-Fi and BLE, Bluetooth Low Energy, do share the 2.4 gigahertz band, NFC and most RFID systems operate at much lower frequencies. In fact, NFC operates at a frequency that is over 170 times lower than Wi-Fi. Holy shit, I was wrong about that. Yeah, okay, so it is 13.5 13.56 megahertz, and then RFID LF is 1.25 to 134, no, 125 to 134 kilohertz. That's crazy. And then RFID HF is 13.56 megahertz, and then RFID UHF, that's crazy. There's different types of RFID here. Is 860 to 960. Why did I think that NFC and RFID is? I'm glad that I looked this up because otherwise I would have given out wrong information. But yeah, okay. Why did I think that NFC and RFID were within the same frequency range as? Well, it might be what Gemini said, that maybe because it's, they are all accessible through our phones. Maybe that's why I thought that. Anyways, so RFID has three different ranges. You have 125 to 134 for one type, as in 125 to 134 kilohertz for one type. Then you have 13.56 megahertz for wait, okay, so So NFC and RFID HF, they share a frequency band. Okay. Then you have another one, which is RFID UHF, which is 860 to 960 megahertz. Now, if I if I'm buying the 838 megahertz module, I think that's a CC1101. Okay, hold on. Okay, so wait, I'm gonna be, see, I said that I wasn't gonna get distracted with other stuff, and now we're getting distracted. Anyways, I'm gonna be buying a CC1101. Which one? No, hold on. I cannot remember. Yeah, this is the shopping list. Okay, yeah, it's the CC 1101. CC101, 838 megahertz RF module for some other RF studies. Would it be possible to tune it to operate on one of the RFID frequencies? How well would that work? Because I was having a conversation about this with Gemini yesterday, and Gemini did mention that while you can tune a lot of these modules that you're going to get, you can tune them to a certain extent. It's not always the best idea because even though they are tunable a little bit here and there, in general, their entire hardware is set up for a fixed kind of frequency range, a very specific frequency range. So you're better off buying something that is meant for that frequency range that you're trying to go for. Okay, in short, yes and no. While you can technically tune a CC1101 module to operate within the UHF RFID range, it is physically impossible to tune it to other. Okay, yeah, true. I wasn't planning on doing the 125 kilohertz and the 13.56 megahertz. Okay, so the UHF RFID is possible. This is where the CC101, no, 110, this is where the module is most at home. Since your module is already an 838 megahertz variant, likely optimized for the 868 European. Have I been calling 868 838? I need to look into that. I need to look into that. Anyways, likely optimized for the 868 megahertz European ISM band. It is very close to, actually, yeah, that's true. If it's optimized for 868, I might be able to tune it to 860. Tuning. The CC, yeah, the module is programmable and can easily be shifted to the 860 to 928 megahertz range via software registers. How well it works. It can act as a basic reader or tag emulator for certain protocols, but it is difficult. RFID protocols often require extremely fast backscatter responses that the module's hardware buffers weren't specifically designed for. You would likely achieve a range of only a few inches to a foot without a specialized power amplifier. A few inches to a foot. Okay, so if we are within the centimeter range, I need to ask this question. Okay, LF and HF RFID, impossible. The CC1101 is a sub 1 gigahertz transceiver, but its internal frequency synthesizer has a hard lower limit. The limit is 300 megahertz. Okay. Hardware barriers. Even if you could trick the chip into a lower frequency, the antenna and matching circuitry on your 838 megahertz module are designed for waves a few centimeters long. A 13.56 megahertz signal has a wavelength of about 22 meters. The tiny trace or whip antenna on your module simply won't see it. Okay, you mentioned a distance for the UHF RFID with the CC1101 838 megahertz. What if, wait, okay, yeah. What if we are talking about what if we are talking about only around 1 meter or less? Because I remember in another conversation we had, you mentioned that while it is possible to tune these chips, it's often not the best idea due to various reasons. I'm wondering if that could cause any issues here. You're exactly right to be cautious. In our previous context, we likely discussed how tuning a radio via software doesn't magically change the physical hardware, such as the inductors, capacitors, and antenna soldered onto the board. However, your goal of reaching 1 meter with a CC1101 tuned to UHF RFID frequencies around 915 megahertz. Wait, did I say however? There's no however written here. Anyways, okay. For your goal of reaching 1 meter, so and so, so and so, so and so, you are going to run into three major real world hurdles: the hardware mismatch, the 838 problem, which, by the way, I do have RFID readers. I just remembered that. I did order RFID modules. I don't remember which range I ordered them for, because I had no idea. I hadn't done too much research on RFID. I didn't even know that there were three different types. I ordered a RFID reader, or a type, and I ordered two of them. And along with that, I got what I'm assuming can be programmed. I'm not sure, because again, I don't understand how RFID works. I'll get to that at some point. Actually, I don't remember if, I think maybe I had ordered something NFC related as well. And I also do have a module, which I had got like ages ago, which is NFC related as well. Anyways, okay. Uh, right. Even though the chip can be programmed to 915 megahertz, the matching network, the tiny components between the chip and the antenna on your module, is physically tuned for 838 megahertz. So the first issue is power loss. When you force the chip to 915 megahertz, the 838 megahertz matching network acts like a filter that blocks its own signal. You will lose a significant amount of power. Uh, you will lose a significant amount of your plus 12 dBm output power before it even reaches the antenna. Then you have voltage standing wave ratio. This mismatch, quote unquote, causes energy to be reflected back into the chip, which can cause it to heat up and reduces sensitivity. Result for 1 meter. You might struggle to get even 10 to 20 centimeters of range because the signal is being choked by the hardware. The duplex dilemma, the passive tag problem. This is the biggest technical gotcha for RFID. Hold on, we can have all of these issues with it, yet earlier I was being told that, oh yeah, you can do it, but like in a limited manner. Like it's within the chip's frequency range, so you can do it. But then now when I'm asking, hey, can problems arise? There's a list of problems that can arise. That's crazy. Okay, this is the biggest technical gotcha for RFID. A UHF reader must transmit a constant carrier wave to power up the passive tag and simultaneously listen for the tag's tiny backscatter response. Okay, the CC1101 limitation, it is half duplex. It can talk or it can listen, but it cannot do both at the same time. Okay. Then the 1 meter goal. To reach 1 meter, you need enough continuous power to wake the tag up. Since the CC1101 has to stop transmitting to listen, the tag loses power and dies before it finishes sending its ID. To make this work at 1 meter, you would usually need a specialized RFID reader chip, okay, or a complex discrete circuit with a directional coupler to separate the outgoing and incoming signals. Then protocol complexity. Okay, you know what? We are not going to try doing this. I do have specialized chips for each purpose for the time being, at least until I've learned my way around, RFID properly, or until I've learned my way around RF properly. I'm not going to attempt to multi-purpose any of the chips. Okay, let's close this before I get distracted again, and let's carry on with this. So yesterday we were looking into traits. We finished reading the trait thing, and here was, okay, implementing a trait on a type. So this is great because I already know this, so I can kind of speed through this section. Hopefully, unless I, run into some kind of issue. Give me a second. Let me open up my stream on my phone. And then we can continue. Uh, yeah, yeah. Just had to open up my chat on the phone, and now we can continue. Right. You use an impl trait name for type name block to implement a trait for a specific type. Did they mention how you create a trait? Oh, yeah, they did. Defining a trait. All right. Then, okay, yeah, you use so and so trait name to implement a trait for a specific type. Okay, so we have the struct news article. We want to implement a summary for it. Okay. Yeah, this is where I was kind of, oh, by the way, yesterday, what I was trying to, the issue that I was trying to reproduce, which I wasn't able to do a very good job of reproducing, I think it might have been, do I have it here? I was trying to reproduce it yesterday and I wasn't able to. I think it was here, right? No, not here. Impl my struct. I think it was here. So I think what I was trying to show was this. So let's do some O1. This is going to give an error because it creates like an empty space within the struct itself, right? But I think this is what I was trying to show. Like, it's the concept of ampersand self versus ampersand self within parentheses, because in this way we are doing a move. So we are reading a reference to self, and through that reference we are accessing A, right? But then we are basically moving A. So if we want to get a reference to that, um, I think we would have to actually this just occurred to me. Let me see if this works. Okay, so we would either need to do this or get rid of the parentheses. And this is one of the reasons why you shouldn't be using parentheses, because when you try to access a member in that way, um, well, it depends if you should or shouldn't be using parentheses. Um, I actually forgot what I was going to say, because I was about to say that, okay, this is why you shouldn't be using ampersand. You should just use self unless you actually want to get the reference. But then I was kind of confused about the point that I was trying to make, because in the past, I think I was trying to understand. I was trying to do research on. I actually have the conversation open over here. Wait, no, not here. I have it open somewhere here, where it was explaining to me. Gemini was explaining to me this thing, and this is where I guess our the operator precedence got brought up, because I was confused about this. I think it was a whole conversation that I had over here. The conversation seems kind of long, so I don't remember what the conversation started with. However, it did eventually come down to this, because I was kind of confused about how the ampersand was working. I think my question, oh yeah, I think my question was, if I do at the rate, not at the rate, ampersand, if I do ampersand self dot A, how does the compiler know whether I'm trying to get a reference to A or trying to move A by getting a reference to self? And I think this comes down to operator precedence. Yeah, I believe this comes down to operator precedence. So what I was trying to show yesterday, which I didn't really do a very good job of reproducing because I couldn't remember what problem I was trying to reproduce or what situation I was trying to reproduce. This is what I was trying to reproduce, and I ended up adding this, which kind of complicated things. Okay, so we're going to get rid of this and move along with this. So we implement the summary trait for our news article struct. Sorry, zoned out. Okay, we implement the summary trait for our news article struct. And here we have the ampersand self. This is something I need to keep reminding myself, because I remember I was kind of, because, okay, when you do the ampersand self thing, right, this kind of becomes like an instance method. So it becomes like a method. Well, yeah, it becomes an instance method, right? As opposed to what I think is called an associated function or associated method. So it becomes the difference between hold on. So we have implemented this here, right? So it becomes the difference between saying my struct o2 dot some function like this versus creating an instance of my struct and then accessing the function. So let's give this, hold on. I don't remember what the field is. This is a string, right? This is a string. So we'll do string, new, just empty string. Yeah. So it's the difference between this versus doing just my struct o2 dot some function. Also, it's not a dot in that case. It's the double colon thing. We access it like this. So I kind of like you can access the function in both of these ways, right? You still have access to the function. It's more about how you end up using the function, right? And because I was looking at it as an instance function versus an associated function, I was kind of the image I had in my mind was different because I think I kept connecting it to C sharp, where you would have static methods versus instance methods. Um, yeah, yeah. I was connecting it to C sharp, where you would have static methods versus instant wo- words. Static methods versus instance methods, because you cannot just access the instance methods by themselves unless you have an actual instance, right? At least in C sharp, that's the case. You can, I don't know if you have access to the static methods from an instance. I don't remember if I have done that. Yeah, I haven't done C sharp in a while, so I can't remember that specific uh, bit of detail. But yeah, um, that's how it works in C sharp, right? But then here you are able to access the function or the method, regardless whether it's an instance or um, being accessed as an associated function. It's just that the way that you work with it kind of changes. Because with an instance, you would then already be passing it. So like it implicitly passes. So you look at the way that some func O1 is called here, there's no self argument given because implicitly it passes this thing in already. Whereas here you would need to pass something in. You would need to create a new. Actually, I was supposed to look into this. I just remembered I had written this down yesterday and I didn't actually do anything with it. I completely forgot about that. Okay, all right. Um, Give me a second. Let me hydrate and then we can continue. Okay. Where was I? Yeah. So we have struct tweet, struct news article. We can implement summary for both of these. Great, awesome. Once a trait is implemented, you can call its methods or instances. You can call its methods on instances of the type, just as if they were regular methods. Yep. Okay. Cool. Practice. Make animals speak. Okay, let's create a speak trait and implement it for how I forgot how oh, I don't have to present I guess I don't have to present my work in this case. I just have to implement the thing and see what the result is. Okay. Um yeah, let's create a speak trait and implement it for different animal structs. Your task, define a trait named speak. Inside the speak trait, define a single method signature, fn speak, okay, that returns a string. Define two structs, dog and cat. They don't need any fields for this exercise. Implement implement the speak trait for the dog struct. Its speak method should return the string woof, and then do the same for cat, but the speak method should return meow. And in your main function, create an instance of dog and cat, and then call the speak method on each of your instances. All right. I guess this is also where I can practice. Uh, I think they're called unit structs, where you don't really have any fields. Let me see. Hold on. Struct dog. Does that work? Yeah, that works. Okay. So we have dog and we have cat. And then here we can create a trait called speak and implement a function called, what is a function called? Speak. All right. Speak ampersand self, and it should return a string. So this should return string new, I think string from, wait, this is supposed to return, give me a second. Its speak method should return that. But the speak method is supposed to return a string, right? Okay, call so and so and print the return string. Yeah, I guess so it's supposed to return a string, and then we can do as str, I guess. Yeah, yeah. Also, why am I implementing it here? It's not supposed to be implemented here. It's supposed to be implemented here. So, impl speak for dog. Then fn speak, awesome. We just return string new or string from. Yeah, string from str. So in here we pass woof. Mismatch type. There's an issue here. Give me a second. Mismatch type. Expected struct string found enum. Hold on, what is from string returning? It returns a result. Oh. Oh. Okay, what does the result contain? Uh, the result contains a string. Okay. I think into works for this, right? No. Unwrap. Okay is for result, right? Yeah, yeah. Dot unwrap. That works. Great. Awesome. Now let's just copy this entire thing. Yank. Paste. Change this to cat. And change the string here to meow. And we are good. Hold on. Oh, yes. We need to also create the... Wait, we can delete all of this. And... Give me a second. Yeah. Let dog equals dog. And then cat equals cat. And I want to do print line dog dot speak. What does this return? This returns a string, right? So then even here, I guess I want to unwrap. Yeah, this returns a string, right? Yeah, yeah. Why is it not giving me an unwrap here? Oh, because this is a string. It's not an enum. So I can just do as str, right? That should work. Are we good? Yes, we are good. So then let's just, oh, yeah. Let's change this to cat speak. And now let's do cargo run. We have an error due to whatever is going on here. So let's get rid of this. And I think we are good now. Yep. Okay. Okay, done. The result is that the program printed woof and meow. I am continuing this conversation now after maybe more than a month. Yeah, holy shit, that's crazy. All right, moving on. Excellent. This means you've successfully defined a trait and implemented it for multiple types. You're building a solid foundation. Now let's connect traits back to generics. This is where traits really shine, allowing you to write flexible yet safe and type-checked generic code. Okay, trait bounds. Actually, okay, before we continue, give me a second because I have something cooking on the fire, and I need to go and check on it and make sure there's enough water in, you know, the the vessel, just so the food doesn't burn. So give me a second. I'm gonna go on BRB, and I'll take a little break and come back. All right, I am back. Okay, so my food is going to be cooking for another like 45 minutes, and at that point, I will end the stream so I can go and take care of my food. Give me a second here. Okay, all right. So let's continue. So now we are getting to something more exciting here, which is trade bounds, I believe. Yes. Okay. Okay. Actually, wait. Let me hydrate first. Then we'll continue. Uh. Okay. All right. So, trade bounds. As mentioned earlier, when you write a generic function, sometimes you need to guarantee that the generic type has certain capability. The generic type T has certain capabilities. You do this with trade bounds. A trade bound specifies that a generic type parameter must implement a particular trait. What's funny about this is that we were looking into this, I think yesterday or the day before, or maybe both, maybe during both streams. We were looking into this, and we extensively looked into this. So then this is yet another thing that we're just gonna kind of speed through, which is great. What more is there after this? Hold on, I'm curious about what you're joking. Okay, all right. Yeah, I'm curious about. Okay, it doesn't mention what's going to be next, but okay. As mentioned earlier, when you write a generic function, sometimes you need to guarantee. I think I read this already. A trait bound specifies that a generic type parameter must implement a particular trait. Syntax for trait bounds. You can specify trait bounds in two main ways. I think, okay, the concept of trait bounds is it's specific to generics, isn't it? Because that's where the whole idea of bounds comes in. Because we don't know the type of a generic when we are implementing, like when we are creating the generic type itself, we don't know what the concrete type is going to be for that generic. Um, and so that's why we have to specify that, hey, we don't know what the type is going to be. It can be any type. However, it must implement these specific traits um, in order to be eligible to be passed into this generic. So I think the concept of trait bounds is specific to generics. I think so. Yeah. I guess we'll find out later on if generics are something. Hold on. I'm curious about this. So we're going to open up a new conversation. Uh, Actually, wait. Just a second. Okay, in Rust, our trait bounds mainly for generics. The short answer is yes. In Rust, trait bounds are primarily used to restrict which types can be used with generics, and then it gives a whole explanation. I was about to say explanation. What? Explanation. Um, then it gives a whole explanation about what generics are and how they work and all of that. Okay, great. Awesome. Let's continue here. So this is the syntax. After you can specify trait bounds. Oh, yeah. Okay. So there's here it's showing us the different ways of specifying trait bounds, which we have looked into. We've looked into three ways of specifying trait bounds, right? One is, give me a second. Okay, yeah. We've looked into a couple of different, wait, hold on. I need to reduce the load on this system, which to be fair, it doesn't have that much of a load, but let's reduce what little load it does have. Yeah, okay, where was I? So we've looked into three ways of introducing trait bounds, right? I'm noticing that one of them has not been mentioned here. So the first method that's mentioned is where we specify the bound, the trait bound, where the parameter is being specified, where the generic parameter is being specified. Another way to do it, and I believe that's if you want to separate trait bounds. Oh, oh, yeah. In that case, you don't have named parameters, right? Hold on, hold on. No, actually, not named parameters. In that case, you don't have named types. So what I'm talking about here is, okay, we can re-implement this function. Fn some func o1, and here we'll do a, and this here we specify impl ord. This is another way to specify the generic type. Another way to do this exact same thing would be this, right? And then we specify t over here. That works as well. And then, of course, there's a where clause. I wonder if this gives us the option for where clause. Move to where clause. There you go. And then if I save it, now it gets formatted and we have our where clause. Okay, awesome. I am curious though why it didn't mention the other way of that impl. I mean, we found out the impl ord way, but I'm curious as to why it didn't mention the other way. Hold on. Let me ask was it here? No, I think it was here. Okay, another thing oh God. Okay, another thing I'm curious about is when using generics is the, well, when using generics for functions, one method of specifying a trait bound is to just use impl trait name after the argument name. I'm wondering if this still counts as the concept of generics, or does this fall under some other category? Also, is this even advisable, or no, is this even good practice, or are the other two methods better? Well, better is subjective, right? But yeah, to answer your first question, yes, it absolutely still counts as generics. Using impiltrate as an argument position in an argument position is what the Rust community calls APIT, argument position infiltrate. It is fundamentally it is fun it is words. It is fundamentally syntactic sugar for the same generic system we discussed. When you write function so and so so and so, the Rust compiler internally desugars it into something almost identical to fn so and so so and so. That's a bit more verbose then, isn't it? Actually, would it be? I mean, whether it's verbose or not would depend on the situation. I don't think it would be considered verbose in all situations. Like, for example, imagine you have taking our summary or taking not ORD. Yeah, yeah. Okay, let's take well, we just defined summary, right? Taking our summary thing into account, or the speak words, the speak thing into account, taking the speed thing into account. Speed? What? Hold on, dude. Words. I'm losing track of my thoughts, losing track of my words. Hold on. Wait. Um, Earlier we did the summary thing, and then in the code for the exercise, we did the speak thing, which is this, the speak trait. Keeping our speak trait in mind, taking that into account, or using that as an example, if we were to define a trait bound like this, in this case, we would have to do it only once, right? However, let's say we had three separate arguments, right? And we didn't specify this t. Just, we are planning on using impl trait bound for this. So we didn't specify t. We are just specifying the trait bound. In that case, we would have to specify the trait bound for A, then the trait bound for B, then the trait bound for C. And like that, it kind of becomes pretty long. So we are better off just shortening it, right? Okay, it still uses monomorphization, meaning the compiler still generates a specific version of of that function for every unique type you pass in. When is it better to use impiltrate? It is considered good practice primarily for readability in simple cases. It follows the rule of least power. Don't use a complex syntax if a simpler one works. Okay, so the impiltrate thing is simple. It's best used for simple one-off bounds where you don't need to refer to the type name again. And then the T trait syntax is when you need to use the same type multiple. So this is what I was talking about. This is the exact example that I gave. And then we have the where clause where you would have multiple different types, multiple different trait bounds for each of the generic types, and putting that into the initial um, the initial parameter declaration can make it can make the signature unnecessarily long. Okay, the one big difference, the turbo fish. This is one technical difference that might affect which one you choose. If you use impiltrate, the type becomes anonymous. This means you cannot use the turbofish operator to manually specify the type at the call site. I don't think I've used the turbofish operator. Um, at all. Hold on, dude. I need to look into this. I need to look into this a bit more. Yeah, I don't think I've used the turbofish operator. I've okay. I don't think I've learned about the turbofish operator. I have used it in like rare situations, but I didn't really dive too deep into what exactly this operator is and what it does. Hey, so this brings me to um, so this kind of makes me curious because um, stepping away from generics, I don't think this is going to step away from generics though. I've never used the turbo fish operator. Um, Tell me more about it. Now, I'm not going to read this right now. This is for off stream, but um, oh, okay. The turbo fish is one of Rust's most famous and uniquely named syntax quirks. It is used to explicitly tell the compiler which type to use for a generic function or struct when it can't figure it out on its own. All right, I'm not going to get too deep into this. We're going to continue with our thing here. Okay, so you can specify trait bounds in two main ways. One is after the generic type parameter, and then the other is using a where clause, especially for multiple bounds or complex signatures. All right. What trait bounds enable? Behavior on generic types. You can call methods on the trait. You can call method. Oh yeah, okay. You can call methods of the trait on the generic type T within the function and compile time safety. The compiler ensures that only types implementing the required traits can be passed to the function. Practice exercise. Generic announcer. Let's use our speak trait and create a generic function that can make any speak implementing type announce itself. Your task: keep your speak trait, dog struct, and cat struct, and their speak implementations from the previous exercise. I'm glad that I didn't delete any of that. Which I mean, I would have just written it again or done a bunch of like undos and gotten back to it. Anyways, define a generic function named announce that takes one argument, item, which is a reference to a generic type T. Okay, okay. Add a trait bound to T such that T must implement the speak trait. Oh, so I'm going to be passing in the dog and cat. Inside the announce function, call the speak method on on the item and print its output prefixed with announcement. If you're in your main function, call announce with both your dog instance and your cat instance. Okay, all right, we can do that. Here's a skeleton. Oh yeah, I don't need to look at any of this. All right, we can get rid of this and do fn announce. Holy shit, dude. We are learning about generics and trait bounds now. This is kind of exciting for me because initially when we first learned about like when I was not even doing the thing through Gemini, back when I was doing it just by reading the Rust manual, the Rust documentation, I was explicitly avoiding anything that had to do with generics. I just didn't want to get into generics at all at the time. And now I'm just like super comfortable with generics, dude. I'm so happy about that. Holy shit. Okay. So T in this case is supposed to be, oh, actually, yeah, okay. T in this case is supposed to be, I'm having one of those moments where I get stuck in that loop of like, hey, okay, I didn't or Gemini didn't teach me this specific thing right now, but like what if I would have come across this in the future and I didn't know about this? And what I'm thinking about is that impl thing, because it didn't teach me about the impl syntax, right? Which it doesn't have to, because that's just one of the, as Gemini mentioned, syntactic sugars. Um, but I guess the answer to that is like if I would have come across it later on, then I guess I would have looked into it and I would have learned that, hey, this is one other way that you can use generics. Right. So in this case, we can do speak. So we need our type to implement speak, and then this is going to be a reference to the type. And it doesn't return anything. It instead prints um, item. It prints item dot speak dot unwrap. No, dot as str. Okay. So now we can get rid of this and get rid of this. And here we can do announce. We pass in a reference to dog. And then we change this to cat. Oh, wait a minute. It is supposed to say something here, right? What was the text? Announcement. Okay. Announcement, so and so. There it is. Announcement woof and announcement meow. All right. Okay. We are good to, wait, what did I just do? Oh, yeah. This exercise will solidify your understanding of how trait bounds allow you to define generic functions that operate on a specific set of behaviors. All right, awesome. Okay, done. It printed out announcement woof and announcement meow. I'm curious if it's ever gonna go into the what do you call it? Turbofish method, the turbofish thing. I don't think it will, but yeah. Okay, what's the last thing? Derivable traits. Oh, yeah, okay, we haven't touched this topic at all, have we? Okay, excellent. That confirms your understanding of trait bounds. That's a core concept in Rust for writing flexible and safe code. Now, for the last part of traits, which is about making your life easier. Just a second. Right. So where was I? Um, Now for the last part of traits, which is about making your life easier. Derivable traits. Rust has a number of traits that are so common and straightforward to implement that the language provides a way to automatically implement them for your custom data types, such as structs and enums, using the derive attribute. Okay? I always assumed that, oh, wait, yeah, I just remembered. Derive. We derive debug and derive display and stuff like that. So like if we derive display, we would then need to specify an implementation of we would need to specify an implementation of the display function so that we can then pass in that type into the print line macro, and it'll know exactly how to do the printing because, well, we have explicitly specified how it's supposed to be formatting the whole thing. Okay, this saves you from writing a lot of boilerplate code. You've probably seen derive debug already if you've ever tried to print a custom struct using so and so in the print line macro. Okay, common derivable words, common derivable traits. Debug enables formatting. Oh, wait, we don't have to implement any of the. Wait. Oh, display is not part of this list. Okay. Display is not a part of this list. So actually, would is debug already let's use my struct here and let's make it i32, and then I'm going to create an instance. So let a my struct o2 a5, then print line, and what is it? Yeah, just a. This doesn't work because my struct o2 doesn't implement debug. Does this work? No, because it doesn't implement display. Now, let's go up here and do the derive thing. I'm just trying to remember if, well, I'm remembering, right? Oh, okay, yeah. So this is what it's for, and then it gives us an implementation. Okay, right. So here we are learning about stuff that's already been implemented for us. So common derivable traits. Debug enables formatting a type for debugging output using so and so or so and so. Partial equal enables the equal and not equal operators for types that can be compared for equality, and then equal indicates that equality is an equivalence relation. If A equals B and B equals C, then A equals C, and A equals B, and then what? No. If A equals B and B equals C, then A equals C. If A equals B, then B equals A. If you implement partial ec, you usually also implement ec if it um, if it makes sense for your type. Then partial ord enables so and so operators for types that can be partially ordered, like floating point numbers, where nan is not comparable. Then you have ord indicates a total ordering. All values can be compared. If you implement partial ord, you usually also implement ord if it makes sense for your type. Then you have clone. This enables creating an explicit duplicate of a value. You call .clone on the value. Then you have copy. This enables bitwise copy semantics. If a type implements copy, then assigning it to another variable or passing it to a function will perform a simple memory copy rather than a move. A type can only implement copy if all its fields implement copy. Then default enables creating a default value for a type using type name default, and hash enables storing a type as a key in a hash map. Okay, practice exercise, deriving. Deriving debug and partial ec. I'm confused about this because I thought we have to implement um, clone and copy. Yeah, I thought we have to implement clone. Let me bring it up here. Let's do clone, save, and before the move occurs, let's do a dot clone. Does this work? Oh, this works. I don't remember what issue I had in the past where I was not able to use clone. Yeah, I can't remember. No, it's not that I wasn't able to use it. It said well, okay, either I wasn't able to use because I was getting some errors, which to be fair, I didn't know too much about Rust at the time. So like now I have a much better idea of what I'm doing. I don't remember if I just wasn't able to use it or if I was required to do some kind of manual implementation of it. But yeah, okay. Let's do this, and now we have that. Okay. Well, all right. I I'm I don't know. I mean, I'm kind of confused about this. I'm gonna have to maybe we don't move on from this real quick. I need to ask certain questions about this thing because this is something that we actually don't know too much about. Um, okay, practice exercise, deriving debug and partial ec. Let's take a simple struct and automatically derive some useful traits for it. Your task, define a new struct named book with two fields, title, string, and pages, I32. Above the struct definition, add derived debug and partial ec attributes in your main function. Create two book instances, book 1 and book 2. Give them the same title and pages. Create a third book instance, book 3, with a different title or pages, and then print book 1 using debug formatting, and then use so and so to compare the two. It should be true, and use so and so to compare the. Okay. All right. Let's do that. So there's a bunch of coding that we have to do here. So struct book, title, string, and then pages, I32. And then up here, we want to derive debug and partial ec. Okay, so now in here, we can get rid of these actually. We don't need any of these. Get rid of that, and then come up here. Let book 1 equals book title some book 01 pages 5. I don't know. What's the exercise exactly? Okay, create two book instances, book 1 and book 2, and give them the same. Okay. All right. Then all right. So we want to give this. What just happened? Okay. Oh, this is supposed to be a string. Oops. Okay. String new, string from, string new, string from. Well, string new can also take No, string new doesn't take. Okay. String from um, str. Let's just put it in here. Some book o1 dot unwrap. And then get rid of this. And let's select this whole thing. Yank. Paste. And paste. That's not, hold on. Yank. Paste. Oh, what just happened here? Okay, yeah. Paste. Dude, I keep forgetting the delete thing in NeoVim is I'm still getting used to that workflow. So we're gonna yank this, we're gonna come here, make sure we are in the right cursor location, and then do that. Okay, great. This is some book O2, and this is book 2. This one is book 3. And we can also give it different pages, 15. Okay, then we print out our, what was the thing? Okay, print out for book 1 using debug formatting. Book 1. Then print line. Here we just want to print whether, what are the conditions? If book 1 and 2 are equal, book 2, does that work? Yes, that works. So we yank and paste, and here we want to check if book 1 and 3 are not equal. So they're both going to be true. Oh, wrong place. There. Okay, awesome. After this, you'll have a solid, wait, this exercise demonstrates the convenience and power of derivable traits, allowing you to quickly add common functionality to your types. After this, you'll have a solid grasp of traits, and we'll be ready for chapter 10, which is lifetimes. Okay, now, I know I said I'll go for another 45 minutes, but I think I should go check on my food. And yeah, I don't wanna risk burning it because I've done that in the past. And yeah, I don't wanna do that. So today we are gonna go raid Louise. Yes, we're gonna raid Louise. Louise is cool people. Louise is pretty chill. Um, I'm gonna start up the raid. I need to run and then check on my food because I don't want that to burn. It's one of my favorite comfort foods. I don't want to ruin that right now. So, okay, that's gonna be it for today's stream. I need to remember to ask this question about, you know, derivable traits and like what the functionality is like and, what all is going on there before I continue with this. But that's going to be it for today's stream. I'm happy about the streak that we have going on. I'm super happy about that, actually. We are currently on like what, day 16, like of continuously streaming. I think so. But yeah, anyways, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.